Hello, and this is Condensed Chemistry with Krista and Ben, and today we will be discussing nuclear theory, also known as the currently accepted theory of an atom structure, through Ernest Rutherford's gold foil experiment. Born in New Zealand in 1871, Rutherford would contribute a whole lot to the world of chemistry and nuclear physics. He attended University of New Zealand, followed by graduate school at Cambridge, eventually studying under a man named J.J. Thomson, who will be mentioned later, where he conducted a multitude of experiments that led him to claiming world-renowned scientific discoveries. Rutherford was known for proposing radiation basics, such as setting forth alpha and beta rays in radioactive decay. He received the Nobel Prize in Chemistry, is the face of New Zealand's $100 bill, and most importantly, for our purposes, was responsible for proposing the correct theory of atomic structure through his famous gold foil experiment.
Before nuclear theory, the accepted theory of the atom structure was known as the plum pudding model, developed by J.J. Thomson, who was Rutherford's mentor. Thomson proposed that the atom was an entirely positive sphere of matter containing negatively charged particles, and no nucleus in the center, similarly to a plum pudding with blueberries stuck to it. Now, Rutherford wanted to test out Thomson's model with what is now known as the gold foil experiment. To make this experiment successful, Rutherford needed a source of alpha particles, which has 2 protons and 2 neutrons. So he utilized a radioactive element known to emit these particles. He placed a radioactive element in an enclosed lead box for shielding against radiation, with a tiny slit of one of these faces of the box so a stream of alpha particles could emit into a piece of gold foil, using the principle of gold films interference as the base of his experiment. He used gold because it can be rolled up very, very thin, and this minimizes the number of multiple collisions between an alpha particle and the gold atoms.
Detectors were coated with a fluorescent substance, so when the particles hit the detector, they flashed. Multiple detectors were placed around the gold film to measure the amount of deflection the particles had. Some alpha particles were deflected slightly, suggesting interactions with other positively charged particles within the atom. Still, other particles were scattered at large angles, while very few even bounced back toward the source. Only a positively charged and relatively heavy target particle, such as the proposed nucleus, could account for such strong repulsion. The negative electrons that balanced electrically the positive nuclear charge were regarded as traveling in circular orbits around the nucleus. He compared the electrostatic force of attraction between electrons and nucleus to the sun's gravity and the planets orbiting around it.
Because only very few of the alpha particles in his beam were scattered by large angles after striking the gold foil, while most passed completely through, Rutherford knew that the gold atom's mass must have been concentrated in a tiny, dense nucleus, proving that his mentor's original theory of atoms being entirely positive spheres of matter containing negatively charged particles was in fact wrong. He later went and created a model representing how atoms actually looked, which was later known as the nuclear model. Thanks to Rutherford's gold foil experiment, we can find out how atoms combine and form many compounds, how atoms collide with each other, and why atoms don't have mass and how atoms disappear. Even though Rutherford proved that the atom was not as Thomson theorized and discovered the nucleus, there are still limitations with his experiment. If electrons continuously revolve around the nucleus, the type of spectrum expected is a continuous spectrum, but in reality, what we see is a line spectrum, unlike his model of orbiting electrons. There's also another problem with his model, because if electrons are constant motion or orbit, they'll have to spend energy to combat the attraction of the nucleus, and eventually they will lose their energy and fall into the nucleus, making the atom unstable.
Additionally, although nuclear theory itself did not generate major environmental issues, Rutherford's discoveries on radiation did eventually become important regarding the use of nuclear energy, which does have an environmental impact. The use of nuclear energy produces radioactive waste, which cannot be eliminated easily and has a very negative effect on our health. In the gold foil experiment, radium was used to generate alpha particles, which does have a bit of an environmental toll.